So our speaker for today is Alessandro Ferragina. He works with Teagasc. He's a research officer at Teagasc, and his work is entitled FT-MIR Predictions and Genetic Study of Milk Technological Properties.
Good morning, everyone, and thank you for being here at this monthly meeting. And today I will present some collection of study that I carried out in my previous activities, and it is about the predictions and the genetic study of milk technological properties. So at the moment, I'm working in Teagasc as a research officer since July 2021. And my research topic is the application and development of analytical technologies for the meat quality evaluation. In particular, I use spectroscopy instruments and hyperspectral imaging. So at the same time, I'm also involved in other collaborations with some colleagues. And one of these, for example, is the use of the spectroscopy for the quality assessment of bakery products. Before to join Teagasc, I was working at the University of Padova, and also there I was using several spectroscopy instruments, several technologies, and I was involved in several studies, and in particular working on the milk quality. And today here I'm going to present, as I said, some results of some works that I did during my activity at the University of Padova. In particular, this is a part of a bigger case study, and here today I will present 4 work packages that were part of this bigger project. So in particular, here I will focus on some important cheese technology, milk technological traits, in particular cheese yield and the recovery of milk nutrient in the curd. These are traits that are really important as indicators of the milk processing attitude, and they're important for monitoring the process, the cheese making process, the milk payment system, and also for the genetic selection. And as we all know, the spectroscopy is a rapid, cheap, and high throughput technique, and it is also already used in the to collect the standard milk recording data. So as I said, I will present some a series of four studies. The first one is about the development of the prediction equation based on the MIR spectra, and to predict these cheese yields and recovery traits. The second work will be to estimate the genetic parameters of the measured and of the predicted traits, and use these genetic parameters as a further validation of this method. And in the third study, what we did is to apply the prediction equation on a population data set of spectral data set. And even in this case, we used the genetic analysis to evaluate this technique on a population data set, for obviously for genetic purposes. The fourth study is mainly related to the first one, and in this case, what we did was to use and test Bayesian models that are commonly used in genomic selection to predict several traits, milk traits. And we compared also the results of these models with those of PLS-based models. So what we did in this in the entire project, what was the idea was to record all the data about the farm management directly in the farm. Then we got also all the milk samples and all the information about all the animals from the breeders associations, and What we did was to process all these milk samples in our lab at the university, where we performed a series of analyses, including these technological traits. There we processed all this data, and we developed also the prediction equations. And we provided all these informations again back to the breeders' associations. The breeder associations use all this data, including the prediction equations, to analyze the milk and provide all these informations both to the farmers and also to the genetics center. So, and the results of this project is beneficial both for the farm and the industry in terms of the quality of the products and for the value of their products. So, moving to the first work. Here, what we did, we used a data set composed of 1,264 individual milk samples of the Italian brown Swiss cows. And these samples were samples related to, were collected in 85 herds located in the northeast of Italy. And for each sample, we had the mid-infrared spectra and also the milk composition. And also we had all the information related to the cows in terms of production, feeding system, pedigree, breeding systems, etc. And here we used 7 traits, in particular 3 measures of cheese yields, the fresh cheese yields, the solid cheese yield, and the water retentions in the curd, and 4 nutrient recoveries from milk to the curd, the recovery of fat, protein, total solids, and energy. So for the data analysis and chemometric, here we used a software that is WhenEasy2 software. This was the standard software used to process the data recorded using the FOSS instrument. That was the instrument used to record the spectrum on the mixed samples. And this is a software that has everything built in, and it's a user-friendly software. And in this case, we used the modified partially square regressions in the software. And we performed also several treatments on the spectra, some scatter correction, first and second order derivatives. We used these treatments alone or also in combination, some of them. And we also used the spectrum entire or removing the water absorption bands that are those that are characterized by the higher variability, and they are considered also to be noisy. For the validation, here we used the 4-fold cross validation with the internally in the software with the random selections of the samples for each group. Here are the results of this study, and as you can see, we got really good results from this study, and except for 2 of these traits, one of the cheese yields and one of the recovery, in particular for the retention of water in the curd and the recovery of fat. And the reason here can be due to the fact that these traits are technological traits. They are not only dependent from the composition of the milk, but there are several factors that affects also the prediction of these traits. And in particular, the physicochemical phenomena that occurs during the milk coagulation and also during the syneresis, and also given to the processing also of the milk. And if we think about this, we can consider the results that we got also for the other traits, really good results. But for example, as I said, the recovery of fat and the water are highly dependent also from all these phenomena that I mentioned. But we can say that given these results, so these predictions can be useful, and they can be used as indicator for the milk payment system and to monitor the processing. Moving to the second work, here we use the same data set described for the first study. And what we did in this case was to do a different validation. This is we did this because we wanted to use all the data available, mainly for the genetic study, also because obviously it's a big data set, but if we split the data set in the training and testing set, then we don't have enough samples to do the genetic analysis. But what we did was to partition the dataset into 3 subsets. The samples were for each assigned to each subset were randomly selected by herd in this case. And what we did was to use 1/3 of the data in the calibration and 2/3 of the data for the external validation. And obviously this was repeated 3 times. The calibrations was developed also in this case as described in the previous work. And what we did here was to estimate the covariance components on the measured and the predicted traits of each test set. And also we estimated the heritability and the genetic correlations as an external validation, indicators of for the external validation, genetic validation, sorry. So now for those of you who are not familiar with the meaning of heritability, genetic correlations, just briefly. So the heritability is the measure of how much the phenotypic variation of a trait can be attributed to a variation of genetic factors. So for example, high heritability means that a trait can be easily exploited for the genetic selection. Instead, for the genetic correlation, it's the proportion of the variance that 2 traits share due to the genetic causes. So for example, if there is a high genetic correlations among 2 traits, this means that selecting for one trait, you can indirectly select for the other trait. So, and here we can see the results of this work. So in particular, the first table on the left, there are the results for the GSILD measures. So here we can see in the prediction results, in this case, they follow the same pattern that we've seen also in the previous study, but the results, the R-squares are lower than the one presented before. And here the reason is mainly, even if the dataset is the same, but obviously what is important here and affected also these results is the type of validation that we did. First, because the number of samples in the calibration set is lower in this case. And also because the validation was done externally, and we take into account also the variability due to the herd. And but I mean, anyway, so we got we can say that we got good results in this case. And if we see also the heritability estimated for the measured and for the predicted traits, we see that they are similar, and we got medium to high heritabilities for these traits. But what is really important here is the genetic correlation. As you can see, the genetic correlations, that means how similar, in this case, means how similar are the measured and predicted traits. We got really high genetic correlations, and they are even higher than the phenotypic correlations. And we can see the same also for the recovery traits. Even in this case, we see a lower value of R-square, and for the same reason described, already described, and also medium to high heritabilities. And even in this case, the genetic correlations were really high. So meaning that even if we have a low accuracy in the prediction of the traits, but from a genetic point of view, these traits are highly correlated with the measured ones. So and this means that from the genetic point of view, so they are significant. moving to the third work, in this case, what we did, we had access to a population database related to almost 30,000 cows of 3 breeds, brown Swiss, Holstein, and Simmental. And in this dataset, we had more than 300,000 milk spectra recorded recorded during the test day, and also the milk composition data. All these records were recorded in 654 hertz. This was the general dataset, and what we did first, we did an editing of the dataset, mainly for the genetic purposes, for being able to perform a proper genetic analysis. And in this table, what you can see is the final dataset, a description of the final dataset that we used in this work. So the first thing that we did was to make a comparison of the spectra, since I say that here we used three breeds, and also the calibration dataset. Obviously, we wanted to compare the spectra of this by breed and also with the calibration dataset. And here you can see, for example, there is the we plotted the average of the spectra by breed and also with the calibration, and also we used the Mahalanobis distances to check also the variability in the spectral set, and we saw that they were similar in terms of variability. What we did in this work, we used the prediction equations developed in the first study, where we used the entire dataset to build the equations, and we used these prediction equations on the population dataset to predict also here the G-seals and the recovery traits. And also in this case, what we did, we estimated the genetic parameters for the predicted traits and also for the milk composition, and we estimated also the genetic correlations among all the traits that we had. So here you can see the results that we got. So here you can see the heritabilities. So even in this case, we got medium to high heritabilities, and similar to the previous study. And they are here in this table. You can see the heritabilities by herd, Holstein, brown Swiss, and Simmental. And you see, for example, that for Simmental we had lower heritabilities. And here I have to say that this difference is mainly due to the heterogeneity of the genetic variants between the breeds. And for example, this is due also to the genetic basis of each breed, because, for example, think that the brown Swiss in the selection scheme is included also, for example, the improvement of the K casein that is important for the to improve the milk processing attitude. While, for example, in the Simmental, in the selection scheme, there is also the improvement of the meat production, and and also there are also other factors that obviously affects the these results, but these are the main one that we have to consider. Then so moving to the genetic correlations, as I said, we estimated the genetic correlations among all the traits, but here what I did, just to because we don't have enough time, I didn't want to show all the data, but I tried to show the most important and significant. So, and what you can see in these two tables are the genetic correlations among the milk fat and milk protein content with the technological traits. So in particular, so we got high genetic correlations among these traits, but as you can see here, so the genetic correlations of the milk fat and milk protein content are not that high with the same traits, the recovery of the same traits in the curve. And this means that selecting for the milk fat and milk protein content, that is what is currently done in the selection scheme. So we're not selecting directly for these traits. I mean, we are selecting because are positive correlation, but in a minor extent respect to the other traits. So, and this means that it is important to if we want to select for these technological traits to include if possible so these traits in the selection scheme. And as we said, this is possible because with the spectroscopy, obviously it gives the advantages that we can predict several traits at the same time. Moving to the last study, as I said, this is mainly related to the predictions here. What we did is we selected 7 traits from the dataset, the same dataset described in the first study, and we selected some composition traits, in particular 3 fatty acids. We selected 3 fatty acids among 47 fatty acids available for each sample. And in particular, we selected the capric, myristoylic, and stearic acid as a representative of all the fatty acids in terms of amount, length of the chain, and also saturated or unsaturated fatty acids. And among the technological traits, we selected the RNA coagulation time, that is another important trait, and also 3 of the traits that we have seen in the previous studies, the CuRGC, protein recovery, and fat recovery. So what we did here for the data analysis and the chemometric, first we standardized all the spectra, centering and scaling for each wavelength. And we detected the outliers using the Mahalanobis distances. And the models that we used in this case were the PLS and MPLS as reference models, and these are the models that were implemented in the WinEC2 software. And the models that we wanted to test here were Bayesian models implemented in the BGLR package of R. And in particular, what we used was a Bayes ridge regression and Bayes A as a shrinkage model. They have Gaussian prior and scaled T prior respectively, and also a Bayes B that is a mixture prior of a point of mass at 0 and a scaled T. This is a mixture prior that operates in shrinkage or variable selection. And in this case, what we did in terms of validation, here we used a training and testing validation procedure. And what we did was to sample 20% of the data, and we selected randomly by heart also in this case, the 20% of the data, and included this data in the testing set. All the remaining samples were used as training set. And obviously, in order to compare the models, we used the same training and testing datasets for all the models. And this procedure was repeated 25 times in order to have all the data represented in the analysis. So here you can see the results of this work, and in this table I presented the results for the 3 fatty acids. I didn't present the results of all the models because the PLS was the one that gave the lower square and was the less accurate, and the Bayes A had the results in the middle between ridge regression and Bayes B. So what I presented, just in order to reduce the data and the amount of data to present, I'm presenting the results of MPLS, ridge regression, and Bayes B. Here for the 3 fatty acids, we can see that the Bayesian models were those that gave the better results, obviously in absolute terms, because if we consider, for example, an increase of 5-6 point of R square, obviously are better results, but we have also to consider and see, in terms of our trait I mean, it is a relative, you know, result. But anyway, so here in absolute values, we can say the Bayesian models were those that gave the better results in terms of R² and of error. And here on the right side of the table is the what you can see in the upper triangular is the percentage of times where the model here in the column gave better results than the model in the row, and in the lower triangular is the p-value results of this pairwise comparison. So, and as you can see here, from of the trace, the base B was the one that was different from all the others, all the other models. Moving to the technological traits, here we can see similar things, even though, for example, for the RNA coagulation times, we have similar results for the ridge regression in base B. Base B was better for the Curtis yield and recovery of protein, while for the recovery of fat, the MPLS was the model that gave the better results in terms of R², while in terms of error, the Bayesian models were those that gave the better results. Even in this case, here we can see so the pairwise comparison, and also here, so for example, for the RCT, there is no significant difference among the two Bayesian models. And here for the Curtis yield and recovery of protein also. So the difference among MPLS and ridge regression was not significant for cheese-yield curve, while for the recovery of protein, the two Bayesian models were not significantly different. For the recovery of fat, we saw that MPLS gave the better results, and in fact here is the model that is significantly different from the others, and it gave better results in general. So something also interesting in this comparison is the study of the estimated coefficients that we got from these models. In particular, here, what we can see for example, for the myristoylic acid, comparing the coefficients that we got, we can see that MPLS and ridge regression that are mainly shrinkage models, so they provided many peaks along the spectrum, while the base B that is operated as a variable selection provided really clear and important peaks. That this gives the possibility also to interpret what we are predicting. You can see the same thing also for the Curtis yield, for example, where also in this case that is a technological trace, and as I said, it depends from the composition of the milk, but not only from that, but also in this case we can try to interpret this data and give a meaning in terms of chemical bonds and absorption bands in the spectrum. So going to the conclusions, so it's mainly the conclusions that I want to give here, and the message is mainly related to the spectroscopy and is related mainly to my experience and what we have seen in this work. And first of all, obviously, is that the spectroscopy is efficient and accurate for the prediction of many milk quality traits, and it can provide a huge amount of traits at the same time, and it can provide the repeated observation on a large number of samples at low cost, which means that this technique is useful also for the genetic selection, and actually it is already used for this, as I said, in the current selection scheme of the milk quality. Then what is really important is the validation. It is fundamental to assess for the assessment of the technology. And what is important is that I think that everyone that applies this technology and develop these models needs to know the dataset first. This is, I think, the first condition. And in particular, it's important to understand what are the source of variations in the dataset. Obviously, the size of the dataset is also important, and also the accuracy of the reference data is fundamental for the assessment of the results. And also it's important for what we need these predictions. What is the use of the predictions? In this case, as I said, there are several applications that can be monitoring of the process, payment system, but also the genetic selection. And as we've seen, so in certain cases, even if the predictions are not highly accurate from a genetic point of view, they are accurate instead. And obviously, all these considerations can help to decide the type of validation that we want to do. And then I want to say also that there are a huge variety of models, spectral treatments, and statistics available. But just thinking about one of the messages of the workshop of the past year, and is also my opinion, is that the simpler is the better. And as I already said, I mean, we have also to consider, if we want to increase the complexity of a model for just increasing a little bit the accuracy. And also, I think that is important where possible to use algorithm statistics and results that are easy to interpret and that can help us to understand also what we are predicting. So I want to say thanks to all the team at the University of Padua, where, as I said, I did all this study. And as I said, also these were just some extract of a bigger study that has been done. And you can find more information also on the publications listed here. And I want to say thanks to Teagasc for giving me the possibility to go ahead with my research. And also want to say thanks to FT-MIR that gave me the possibility to present here today. And thanks also to Maria Alessandro for organizing everything. So, and thanks to all of you for the attention.
Thanks, Alessandro, for your presentation. It's nice to see how we can also use the predictions from the MIR. Sometimes we just do predictions and then we stop there, while one of the real interest is how to use our predictions after getting the predictions. So yeah, thanks again, and also for the conclusions from your personal experience. If there are any questions, please mute yourself and ask. First question, because it is related to a work I'm currently doing now. You saw that when you validated your informations across herd, you slightly, your coefficient of determination slightly decreased. So the question is, do you think that if you see this sort of decrease in your coefficient of determination means that your prediction equations are not generalizable? So like when you have your informations, you have data from completely new farms. The question is, are that informations and your prediction model reliable when applying to completely new farms, or what do you thought about that?
So, well, I think that first of all, we have also to keep in mind that what is important, in spectroscopy is the variability that we have in our data set, and okay, when we use only one data set, to perform all this data, obviously we are limited to the variability of that data set. And that's why there is important to understand what kind of validation to do. But you are saying, okay, we develop calibrations and then we use them on an external data set. But it depends, probably where that new data set, falls in terms of variability respect to the data set that we use it to build our equations. But I mean, as I showed here, it's important the variability, when we know the source of variability. So there, the accuracy decreased because we took into account one source of variability that we know is important in our data set, And yes, I mean, what is important is to check the variability of your data set. I think is one of the first things to do. Because sometimes what we do, we develop calibrations and we say, okay, these are good for everything. Instead, probably it's not, because you have always to be in the conditions to think that probably the data set that you will use, because this is what is normally done, you know. And in fact, the big companies that produce these instruments that provide calibrations, obviously they develop their calibration using really huge data sets of thousands and thousands of samples in order to increase the variability as much as possible. So now I don't know if I replied to your questions or I gave you an idea or I made it more complex.
No, it's okay. It's okay. Thanks. Okay, I have also another question because I don't know what's the difference between partial least regression, modified partial least, like if you know modified partial least regression, because I never really heard about that, so I don't know.
Okay, well, this is a good question. Thank you for that. Now I have to say that the last study we decided to do it also because of this, you know, and why I used, for example, the WNEASY software to develop the calibrations there instead of performing the PLS using R also, for example. That's because, for example, many times using this software, you don't know what they do inside because they are like boxes, you know, they are user friendly, yeah, right? It's easy to use them, but what they do, you don't know. Now, to be honest, for example, I don't really know what are the difference among MPLS and PLS that WNEASY2 does. In fact, when I did that work, I did also a question, you know, in ResearchGate, trying to find someone that knew what the MPLS does in WNEASY. And to be honest, I didn't find any answer to that, you know. Now, probably it is, you know, I found something, and it seems that the MPLS, what it does is just a selection of a portion of data, you know, that are more variable or more representative of all the spectra that are in the data set. Is a kind of local calibration, for example, you know, as I understand, but using a data set selected in a certain way. But to be honest, you know, I don't know exactly, still now, I don't know exactly what the MPLS of WNEASY2 does, you know. I saw only that the results were better, you know, respect to the PLS, and that's it. But many times it's not easy to understand. And obviously, they don't tell you probably, you know, because they are their secret also of what they do inside. So, but I don't know if someone here knows what MPLS does, but I mean, to be honest, I don't have it clear at the moment.
You know, that's a good point, like, because sometimes I find that, like, mainly at the start working with the data, it's like, oh yeah, we're user-friendly software. Yeah. So it's better, like, I don't know much about chemometrics, I'm going to use user-friendly software. But yeah, when you start using user-friendly, you don't know much about what's going on. When you move to more software where you have to code, you really start to know what's going under. But yeah, it needs time to learn coding. Yeah, but there you understand what you are doing, at least, you know, and you are able also to interpret your results. So that is important, I think, you know, here, since here it's important also, as I say, we need to understand what we are doing, and we need to be able to interpret the results in terms of spectra. You know, many times, for example, I showed the plot of the coefficients, and those are important because there is something that probably you didn't notice here. In these plots, I don't know if you see them. I show you. I share again. Wait.
To add to it, actually, I found once the paper about this modified.
Yeah. So, for example, this plot here, if you notice, all the coefficients are positive, you know, obviously, because here what I did at the time was to standardize them and make in the absolute value. But here what is important is also, and here I didn't plot it, is to plot, let me see, okay, is to plot at the same time, for example, the spectrum, you know, because here I see, okay, this is a huge peak in this position. But it's important to see what the spectrum does in this position, because if this is a positive value and I have a negative spectrum, is something, you know, if this is positive and the spectrum is positive. So this helps to understand also in terms of the final results, you know, each wavelength, and each coefficient in what terms it contributes, you know, to the final results are small things, you know, but I think these are important to understand, you know, what we are doing, to interpret what if it's another kind of validation, you know. I want to see if what I'm predicting, if I'm predicting protein, for example, you know, I want to see if in the spectrum, so I'm selecting on, I'm working on the chemical bonds related to protein, because if I'm predicting something, probably in the future in other dataset, my prediction equation doesn't work, you know, because in my dataset I'm predicting protein. Okay, it works for protein, but it's not protein what I'm predicting. This is the risk, you know, and mainly with the technological traits, because as I say, they don't depend directly only from the composition, but also from other parameters, let's say.
I had a question about the first part, WP first, like the first working package. And as far as I understood, you used around 1,200 samples.
It's 1,200 samples, about 1,200.
Yeah. So, but how much cows it was?
1,200 cows, because they were individual milk samples. So one milk sample for each cow.
Okay, I see. And when you did the cross-validation in that case, do you control that the same cow will be always in the same?
No, this is what I said. So there, the 4 validation groups were randomly selected internally in the software, and you know, one cow probably was always present in the calibration set, you know. So there I didn't have control of the.
So it was possible that the same cow was in the train and the testing data set.
Yes, it's possible. Yeah. Again, here, you know, is always talking about these boxes, you know, that are user friendly, but sometimes you don't know what they do inside, you know.
Yeah, I see. And another thing, so you mentioned that for each cow you also had some additional data, but I don't remember what exactly was that. Maybe weight and something.
Well, for each cow we had a lot of data, because I said that this was a huge case study, you know. For example, we got all the informations, also, for example, geographical information about the pasture, about the feeding system, you know, for each cow. And then for each cow we had all the informations useful also for the genetic analysis. So all the pedigree, you know, now I don't remember all the data that we had, but we had a huge amount of data.
But did you try to train a model using that data?
I mean, to make a kind of data fusion, adding together the spectral data and also data about the cow.
I mean, yeah, or that data alone, or data plus spectra.
No, we didn't try, you know. We started from the basics, you know, first using one thing, but we didn't try that time.
Okay. Yeah, I guess that was it. Yeah, thank you.
No, thank you.
I would like to thank Alessandro for your presentation. And
thank you for giving me this possibility to share with you this work.
Yeah, if you think about other questions, or if you hear this presentation as recorded, feel free to write directly to Alessandro. And yeah, as you know, our monthly meetings are now online. So we have a page on the FT-MIR website where you can find the future speakers or the recorded version of the presentations. And yeah, like if you also, like we have a mailing list where I send all the information about these meetings. If you're not in the mailing list and you want to be added, feel free to send me an email. I'm going to write my email to the chat. And then, yeah, for the rest, thanks again all for participating and for the questions.
Bye, everyone.